So I'm not going to lie, today is pretty hard. It's the last content, and it is like one of the, probably the trickiest stuff. So yeah, don't be too worried if you can't keep up, because it is hard. Just letting you know. Okay, so number one, if 75% of the ionizing radiation from a source is stopped by a 2 centimeter thick sheet of lead, how much would be stopped by a 3 centimeter thick sheet of lead? So these percentages are just numbers that you need to recognize. Okay, so I'm going to draw a 1 centimeter thick piece of lead. Okay, so this is 1 centimeter, and we have, let's say, 100% coming in. 100%, it's going through this layer. Now, some of the radiation is going to be blocked by this sheet of lead, this 1 centimeter thick piece of lead. Now, there's going to be 50% of the incoming radiation. So 50% of the 100% that's coming in is going to be absorbed. Okay, so if 50% is absorbed, then only 50% will get through to the other side. Okay, so now we've got 50%. Now we're going to draw our second piece of lead, which is also 1 centimeter. Now, so we can assume that this second piece of lead is also going to block 50% of the radiation that comes in. So it's going to go through, and 50%, and this time there's only 50% coming in, so that's 50% of 50% that's absorbed or blocked. Okay, so that means that 25% of the total is going through. So now there's 25% that has gone through the second layer. Okay, so how much has been stopped? So 50% of the total was stopped after the first layer, and then 75% of the total was stopped after the second layer. Okay. Now you need to be able to recognize 50% and 75%. Okay, and they're usually going to make it like recognizable numbers. Okay, so now we're going to have our third centimeter. So 1 centimeter here, and again it's going to block 50% of the radiation that comes through. So there's 50% of 25% will be absorbed. Okay, so that means that only half of 25% will get through, which is 12.5%. Okay, and if only 12.5% is getting through, it means that 87.5% has been stopped. Okay, so those are just numbers that you need to recognize: 50%, 75%, 87.5%, and also 50%, 25%, 12.5%, and it could go on to 6.25% as well. Okay. Number two, so the answer there would be C, 87.5%. Number two, we have a 2 centimeter thick sheet of lead, which blocks 75% of the radioactive rays, and that means that only 25% is transmitted. So we have this situation here right? So we've got 75% blocked and 25% getting through from 2 centimeters. And so you only want to let 12.5% through. So we know that if we make each centimeter of lead is blocking 50%. So then another centimeter would drop the amount that's transmitted down to 12.5%. So the answer here would be 3 centimeters. Okay. So number 3. Number 3, if 75% of a large sample has decayed after 2 hours, what percentage of the sample that remains will decay in the next hour? Again, you have that number 75% and 2 hours. So I'm assuming you guys know what the half-life is, but the half-life, I'll just quickly explain it. So this is the symbol for half-life, T half. Okay, so that's the amount of time for half of the sample to decay. Okay, so if you start off with 100, after 1 half-life, you start off with 100%. After 1 half-life, what's it going to be? What's it going to drop down to? Yep, 50%. And then after 2 half-lives, what's it going to become? Yep, 25%. And then 3 half-lives, it's going to be 12.5%, and so on and so on. Okay, so you just need to be able to recognize these numbers, and you just have to recognize that if 75%, so in this case there'd be 50%, after 1 half-life there'd be 50% remaining. After, 50% decayed. So 50% remaining and 50% has decayed. And then after 2 half-lives, 25% is remaining and 75% has decayed. And after 3 half-lives, 12.5% is remaining, and that means that 87.5% has decayed. Okay. Now this one's worded quite particularly. So it says what percentage of the sample that remains will decay in the next hour. So we should have been able to deduct from the first part of the question that 1 half-life is 1 hour. Okay, so we know that T half in this question is equal to 1 hour. Okay, so in the next hour, 50% of the remaining samples should decay. So your answer here is going to be C, 50%. So next question. Number 4. If 75% of a large sample has decayed after 2 hours, then what percentage of the original sample will remain after a total of 4 hours? Okay, so you can see how the same sort of questions recur. So you've got 100% after 1 half-life. We know that 1 half-life must be equal to 1 hour, right? Since 75% has decayed after 2 hours. So 50%, 1 half-life. After 2 half-lives, it'll become 25%. After 3 hours, or 3 half-lives, that's 12.5% remaining. and then after 4 half-lives, it's going to become half again, which is 6.25%. Okay, so your answer will be A. Okay. Does anyone have any questions about that? So it's, yeah, relatively simple once you know what you're doing. Number 5, technetium has a half-life of 20 hours. What is the activity of 4.25 milligrams of this technetium, and you want the activity to be in curies. So activity. So the activity of a sample is A, has the symbol A, and that's the number of decays. So they could say decays or disintegrations. The number of decays or disintegrations per second. Okay, and that's going to be in becquerels. Which is BQ. Okay. So activity is the number of decays per second in becquerels, and that tells you how many molecules or how many atoms are decaying per second in the sample. Now, one becquerel, we have another unit for activity, and that's curies. So one curie, so this is named after the Madame Curie. That's the symbol for Curie. So 1 CI is equal to 3.7 times 10 to the 10 becquerels. So you need to know that. And when you do activity, you have to have your activity in becquerels, not curies. Okay? Unless you want your answer to be in curies, then you can just use curies, but otherwise you're going to have to convert into becquerels. All right? Because 1 becquerel is 1 decay per second, whereas 1 curie is not. It's a much bigger number. Okay? So this one's a lot of steps, so I apologize in advance. So we want the answer to be in curies. So that means we're going to have to convert it at the end. So I'm just going to rub this off so I can have some space. Right, so here's the equation for activity. The activity is equal to lambda. So this is not wavelength. When we're talking about activity or decay, this is going to be the decay constant, okay, multiplied by big N. So that's the number of molecules in the sample. Now, you can find the decay constant. The decay constant is equal to 0.693 divided by the half-life. And the half-life is going to be in seconds. Okay. So 0.693 divided by the half-life, which is 20 hours. So 20 times the number of seconds in 1 hour, which is 3,600. If you do that, your decay constant is 9.625 times 10 to the negative 6. Okay, so that's your decay constant. And then you need to find the number of molecules, but what you have is the mass. So first of all, you need to find out the number of moles in that mass. Okay. Now technetium, so it's 9543, that top number. The top number is your mass number. So the molar mass is equal to 95 grams per mole. Okay. So we want to find the number of moles in 4.25 milligrams of technetium. So from chemistry, you'll know N is equal to the mass divided by the molar mass. So it is 4.25 milligrams, or 4.25 times 10 to the negative 3 grams, divided by our molar mass, which is 95. And that will give you 4.474 times 10 to the negative 5 moles. So we have that number of moles in the sample. Now we have to turn the number of moles into the number of molecules. Okay, so remember there's Avogadro's number in 1 mole. So then we want the number of molecules, which is equal to the number of moles multiplied by Avogadro's number. So that's 4.474 times 10 to the negative 5 times Avogadro's number, which is 6.02 times 10 to the power of 23. So Avogadro's number is also in your formula sheet. And that will give you 2.693 times 10 to the power of 19 molecules. So that's the number of molecules. So now we have both the decay constant and the number of molecules. So now we can plug these numbers into our original formula to get our answer, our activity in becquerels. So decay constant times the number of molecules, that's 9.625 times 10 to the negative 6 times our number of molecules, 2.693 times 10 to the 19. And that's 2.59 times 10 to the power of 14 becquerels. Okay, but we don't want our activity to be in becquerels. We want it to be in curies. So remember we said that 1 curie is equal to 3.7 times 10 to the 10 becquerels. So we want to turn becquerels into curies, so we have to divide this number divided by 3.7 times 10 to the 10, and that will give you 7,000 curies. Okay, so your answer is D. So it's a lot of steps. Yeah, unfortunately. Whew, okay. Number 6, we have uranium decaying by alpha particle emission with a half-life of 4.5 times 10 to the power of 9 years, 4.5 billion years. What fraction of a mole of uranium will remain after 4.0 times 10 to the power of 9 years? So we have the half-life, which is 4.5 times 10 to the power of 9 years, and we have the time which has passed, which is 4.0 times 10 to the power of 9 years. Okay, so when they ask you how much is remaining after a certain time, then you're going to use this equation. So the number of moles remaining at time t, so the number of moles remaining at time t is going to be equal to the original number of moles when you started, multiplied by E, so that's Euler's number, and you can get that by doing shift ln on your calculator. Okay, e to the power of negative decay constant multiplied by the time. Okay, so we want the fraction of a mole, so we'll just say that our NO was equal to 1 mole. Okay, and then whatever our answer is our fraction. Okay, so we need to find out the decay constant. So the decay constant is equal to 0.693 divided by the half-life. Now here we have the time in years, so we can leave our half-life in years as well. So if you're going to use time in years, then you can use years for your half-life. They just have to be in the same units. So 0.693 divided by 4.5 times 10 to the 9, and that is 1.54 times 10 to the negative 10. So that's our decay constant. So we can plug that now into our formula. So we started off with 1 mole times Euler's number to the power of negative decay constant, which is 1.54 times 10 to the negative 10, times the time which has elapsed, which is 4 times 10 to the power of 9. Okay, and that should give you 0.54. All right, so that number makes sense because it's nearly been 1 half-life. So after 1 half-life, 50% will decay, or 50% will be remaining, but it hasn't been quite 1 half-life yet, 1 full half-life. So it's just over 50% remaining. Okay, so your answer should make sense as well. So on the cheat sheet, I don't actually have this one. I have the number of molecules at time t is equal to the original number of molecules multiplied by e to the negative decay constant times time. And you also have mass at time t is equal to mass original times e to the power of negative decay constant times t. And then you also have the activity at time t is equal to the original activity multiplied by e to the negative decay constant times t. Okay, so you can choose to have all 4 of these on your cheat sheet, or you can just have one and just say the quantity at time t is going to be the original quantity multiplied by e to the power of negative decay constant times t. Okay. Number 7, we have a sample of radioactive material weighing 2 kilograms and a half-life of 2 hours. The sample produces beta radiation at a rate of 5.8 times 10 to the 21 counts per second. So that number there, 5.8 times 10 to the 21, that's going to be your activity. So remember, your activity is the number of decays or disintegrations per second, and that's what that beta radiation is, the counts per second. So we know that the activity is equal to 5.8 times 10 to the 21. And so the unit for that will be becquerels, BQ. We want to find the decay constant. The decay constant is just 0.693 divided by the half-life. So that has to be in seconds. So 0.693 divided by 2 hours times the number of seconds in 1 hour, which is 3,600, is going to be 9.6 times 10 to the negative 5. So that's your answer, option A. Now we want to find out how many radioactive nuclei there are in the sample. So that's the number of molecules that we want to know. Okay, so we want to find out n is equal to question mark. Now our equation is activity is equal to the decay constant multiplied by the number of molecules. Okay, so we want to find n. We want to find this. So it's going to be n is equal to the activity divided by the decay constant. So we said that our activity is 5.8 times 10 to the 21. Our decay constant, we just worked it out. It's 9.6 times 10 to the negative 5. So that will be 6.0 times 10 to the 25. Okay, so there's this number of molecules. And remember that each molecule will have one nucleus, so that's the number of radioactive nuclei. All right. Cool. Number 9. So we want to find the energy of the K alpha X-rays produced by a tungsten target. So the symbol for tungsten is W, and it shows that the number of protons, the atomic number, so that's Z. Z is equal to 74. Okay, so it means it has 74 protons in the nucleus. And we want to find the energy in kilo electron volts. So you've got K alpha, so I'll quickly show you what K alpha is. You've got your nucleus, right? And then you have your first energy level, your second energy level, right? And your third, and so on. So this is n equals 1, n equals 2, n equals 3. Okay, so we can also call the first electron orbital K, the second one is L, and the third one is M. Okay, now if you have so whenever you have an electron coming down to this first orbital, we call it K. Okay, so if you go from the second orbital down to the first orbital, that's called K alpha. Okay, and then if you go from the third orbital down to the first orbital, that's called K beta. Okay, and if you went from the third orbital down to the second orbital, it's coming down to the L orbital, so you call that L alpha. And if you had another one on the fourth orbital going down to this one, you'd call that L beta. Okay, so I'm just letting you know what that is in case you're curious, but you don't have to know any of that except for K alpha. Okay, so that's the only one they ask about. And so when you have this change in energy level, you're going to have a change in energy, right? So there will be a change in energy between these two orbitals, and that energy is released as a photon, and this photon is your X-ray. Okay? So this the energy released, or the photon released from the K alpha, is your X-ray. So it's really quite simple. So then your equation for K alpha, delta E for K alpha is equal to 10.2 times EV multiplied by Z minus 1 squared. And remember that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So when we want our energy to be in joules, we're going to replace this with 1.6 times 10 to the negative 19. But if you look at the question, we want the unit to be in kilo electron volts. So we're just going to, so we just want it in electron volts. So that means that we don't have to put in 1.6 times 10 to the negative 19. So that's 10.2 times Z, which is 74 minus 1 squared. Or you could just write 10.2 times 73 squared. Okay, and that's going to be 54,355 electron volts. Okay, and that's equal to 54 kilo electron volts. Right. So the only thing you need to know is Z. So it's really easy. The next one is the same thing pretty much. So number 10, what's the energy of the K alpha photon produced by an X-ray using a copper target where Z is equal to 29? So that's the number of protons in that nucleus. So, and we want the answer to be in kilo electron volts. Okay, so that means we don't have to put in the EV. So it's 29 minus 1 squared. So that's 7,996 electron volts, which is 8 kilo electron volts. All right. Number 11. So now we want the wavelength of the K alpha characteristic X-ray emitted from a silver target, and we want that in nanometers. Okay, so remember that the X-ray is a photon. So the X-ray is a photon. So a photon will have a certain amount of energy. So it has energy, and so it will also have a frequency. It will also have wavelength, and it will also have momentum. Okay, so so here we know we know that it's a K alpha, and we know the number of protons, which is 47. So Z is equal to 47 So that means that we can calculate the energy of that photon or the X-ray, and then we can use the energy to find out what the wavelength is. So we're going to calculate the energy of the K alpha X-ray, which is 10.2 eV Z minus 1 squared. Now this time, because we're wanting to find the wavelength, we need to have our energy in joules. Okay, so that means that we're going to now put in, replace EV with 1.6 times 10 to the negative 19 times Z minus 1, so Z is 47, and that will give you your energy in joules, so that's 3.453 times 10 to the negative 15 joules. Okay. And then your energy is equal to H times C over the wavelength, and we want the wavelength. So wavelength is equal to HC divided by E. So we're just going to swap those around. So on my cheat sheet I just have, so H is, H is equal to 6.63 times 10 to the negative 34, that's your Planck's constant, and C is equal to 3.0 times 10 to the 8. Now you can just multiply them together, so HC is equal to 1.989 times 10 to the 25. Okay, so that's probably going to be easier if you have that number on there, because you'll probably use it enough. So that's 1.989 times 10 to the negative 25 divided by the energy, which is 3.453 times 10 to the negative 15. And that's, the wavelength is 5.76 times 10 to the negative 11 meters, and you're going to divide that by 10 to the negative 9 to turn that into nanometers. So that will be 5.76 times 10 to the negative 2, which is close enough to option A. Okay, I'm not really sure why it's a little bit off, but I think there's like other equations that you can use as well. But yeah, that's close enough, and that is the right answer. I've checked. Okay. Yep. Oh, yeah, this is to the negative 25, sorry. Okay. Next, we want the frequency of the K alpha characteristic X-ray, or in other words, the photon. So we can find the K alpha energy of the photon. So it's exactly the same thing, 10.2, and we want that to be in joules. So we're going to replace EV with 1.6 times 10 to the negative 19. And the Z is equal to 78 this time. And that's 9.676 times 10 to the negative 15 joules. So we want the frequency. Energy is equal to HF, so that means frequency is equal to E over H. So 9.676 times 10 to the negative 15 divided by our Planck's constant, which is 6.63 times 10 to the negative 34. And that's 1.46 times 10 to the power of 19 hertz. Okay. So if they ask you for K alpha wavelength or frequency or momentum, you're just going to find out the energy first, the K alpha energy, and then turn that into momentum or frequency or wavelength or whatever they want. And that has to be in joules. Okay. Number 13, we have a 1 kg carton of milk, which is irradiated with 5 mega electron volts of beta radiation. In the process, 0.5 joules of energy is deposited in the milk, and we want to find the absorbed dose that's received by the milk in the unit grays. Okay. So the absorbed dose, so the equation for that is the energy that's absorbed, so the radioactive energy that is absorbed, in this case that's going to be 0.5 joules, and the mass of the milk is 1 kg, so that's 0.5 over 1, which is just 0.5 grays. Okay, so GY is gray, that's a unit of absorbed dose. So your answer is option B. And then you want to find the dose equivalent. So they can say dose equivalent or the effective dose. Okay, so those two mean the same thing, dose equivalent or effective dose. So essentially, there's different types of radiation. You have, so the types of radiation, there's alpha radiation, so which is when you're getting hit by alpha particles. So we talked about alpha particles last week. I hope you remember what they are. So that's 2 protons and 2 neutrons, right? Okay. So if you get hit by one of those, it's pretty bad for you. Okay. So that's alpha radiation. You can also have beta radiation. So beta radiation, we talked about beta plus and beta minus decay. So that's going to be positrons and electrons. If you get hit by those, it's pretty bad for you as well. And then you can have gamma. Gamma and also X-rays. X-ray radiation. So if you get hit by gamma photons or X-ray photons, that's also going to be not that great for your health. Okay, so we have something called the relative biological effectiveness or relative biological effect, and that's your RBE. Okay, so depending on what type of radiation it is, the RBE is going to be different. So for alpha, it's equal to 20. Okay, so the alpha particle is quite large and it's also charged, so it has quite a big impact. And then beta is 1.7. Okay, so it's not as bad for the same amount of dose. And then for gamma rays and X-rays, they have high energy, but they pretty much just tend to pass straight through you. Okay, so it's not as damaging as alpha particles. Okay, so sometimes they give you the RBE in the questions, but then sometimes they don't. So if you look at this question here, you'll notice that they haven't given you the RBE of beta radiation. So unless you remember that beta radiation, the RBE is 1.7, you're not going to get the right answer here. Okay, so it's probably a good idea just to write them down on your cheat sheet. Okay, okay, so the dose equivalent or effective dose takes into account what sort of radiation you've got. So it's going to be your absorbed dose multiplied by your RBE. Okay, so our absorbed dose was 0.5, and our RBE is beta radiation, so that's 1.7, and that's going to be 0.85 sieverts. Okay, so that's sievert. That's your unit for effective dose. Okay, if you're unsure whether they're asking for absorbed dose or dose equivalent, then you can look at the units that they're wanting it in. Okay, so if they say grays, that's the absorbed dose, so that's just energy divided by mass. And then if they want it in sieverts, that's going to be, you're going to find your absorbed dose first, and then you're going to multiply it by the RBE. Okay, is that pretty clear? As clear as it can be. All right, well, that's the end of the basic tutorial. We'll start again in 10 minutes at 8:30. Okay, cheers. Yep.
They're not alpha, or like.
Never
mind. The other question is this one.
Yep.
You said like if it's half time, it's going to be 50. If it's 2 half time, it's going to be 75 meters.
Yep.
Yeah. How do you know the next hour? Isn't it should be like this one?
Well, it says what percentage of the sample that remains. So there's 25% remaining, and of that 25% that's remaining, 50% is going to decay, because that's one half-life. 1 hour is one half-life.
So they're just asking how much it's going to be decay after?
Yeah,
right?
from after 2 hours to 3 hours.
It's
so
always going to be 50%, right?
Yeah, for this, how they've worded it here, what percentage of the sample that remains will decay in the next hour. So you know that in 1 hour, half will decay.
Yep.
Yeah, so that's why it's option C. But it is a bit confusing, because yeah, I when I first read it, I was like a bit confused as well.